Hello. Here is another straightforward problem from your Chapter 11 homework. It's much like the skateboard problem, but with one added complication. In this problem, we have to deal with relative velocity. So we're told that there's a football player who, for whatever reason, is sliding across a frictionless, icy surface. So he's out roller skating. That's not something you see every day. Football players, not roller skating, ice skating. Football players and ice skates. And we're given his initial speed. Let me write that down. He is flying along at a modest 2 meters per second while holding the football. So that's something like 5 miles per hour. He's 70 kilograms, which is definitely on the low side for a football player. And his football weighs about 1 pound. And then he chucks the football. I goofed up with the drawing, so just ignore that. Here's the football. And we're supposed to figure out how fast he's moving after throwing the football. Let's think about this in terms of forces first, just from an F equals ma dynamical perspective. In order to accelerate the football, I mean, the football is moving at 2 meters per second, and presumably it's moving quite a bit faster after that. So the football sped up. That doesn't happen without a force. So he had to push on the football in this direction. Newton's third law tells us that the football would have to push back on him in this direction. So since the force on the football player is opposite the player's velocity, we know that the player is going to slow down. Now, how much is he going to slow down? Most of you have thrown a football or something like that, and you have a sense that the amount of force developed between your hand and the football is not enough to make a significant change in your speed. But we're also not accustomed to throwing footballs while ice skating, so it's not real obvious just how much you can slow yourself down by doing this. So, of course, we're going to use conservation of momentum, because after all, this is chapter 11, and there must be some reason that the person who wrote the problem chose to put them in ice skates on a frictionless surface, because we can treat the ball and the person as a closed system. And I'll say F external in the x direction is 0 because there's no friction. We're not worried about air drag at this modest speed. And that means there's no force on this system from the outside, at least not in the x direction. There is going to be the normal force supporting their weight, and then there's gravity, but that's the y-axis. That's neither here nor there, because we're not talking about the y-axis. So this means that capital P, the total momentum in the x direction, is a constant. That's how we're going to solve this problem, or that's one approach to the problem. So you could either start with this. You could say px at time 1. I'm using time 1 for before he throws the football. Time 2 is after he throws the football. The total momentum at time 1 should be the total momentum at time 2. That's one way to start this problem. You would just plop in the two separate momenta, ball and person, ball and person. Or you could use the approach that I often prefer. You could say that the change in lowercase momentum experienced by the player, momentum of the player, is equal and opposite to the change in momentum experienced by the ball. Now, I haven't bothered to write the subscript x now because this is just a one-dimensional problem. It's understood, or you should understand. You should understand from the context that we're talking about momentum conservation in the x direction. Okay, so in part A, what they tell us is after the ball is thrown, it's moving at 15 meters per second. That's over 30 miles per hour relative to the ground. So I'll say the velocity of the ball at time 2 is equal to 15 meters per second. So here's the notation I'm going to use for this problem. If I just put which object I'm talking about and which time, it's understood that that velocity is specified with respect to the ground. Remember back in chapter 4 when we talked about reference frames and relative velocities, we had to say things like velocity of the ball with respect to the ground, VBG, velocity of the ball with respect to the person, VBP. I'm going to avoid that notation for this particular problem because we've already got these extra subscripts for the times. But it's understood this is how fast the ball is going with respect to the ground. So find the velocity of the player at time 2. Well, velocity is part of momentum. So if I just enforce this condition, I should be able to find that velocity It would have to be the only unknown in that equation. And remember, there's no new physics here. This is really just Newton's third law and Newton's second law combined with some calculus. Okay, so I will say, I'm just going to implement this. Since the masses are not changing, delta P for the player would be mass of the player times delta V of the player. That's got to be the negative of mass of the ball times delta V of the ball. Again, I'm implementing this equation. Since I'd like to find the final velocity, then I really ought to solve for delta V of the player. So that would be negative, take the ratio of the masses, multiply by the change in velocity for the ball. Okay, well, the ball's mass is a piddly 0.45. Compare that to 70. And we already see something that makes sense. Because the person is so much more massive than the ball, this ratio is considerably less than 1. That means the player's change in velocity will be much less than the ball's velocity or change in velocity. And you know what? That's really just an alternative statement of something we saw at the beginning of the semester. This is another way of saying that for a given force, the more massive somebody is or something is, the less it accelerates. Because didn't we get this by integrating F equals ma? It's like the integrated version of that same statement. You could either say that more massive objects accelerate less, or you could integrate with respect to time and say more massive objects experience a smaller change in velocity. Okay, the change in velocity for the ball, let's be careful with signs. Well, we're told that afterwards it's going 15, so that's the final velocity. And the initial was the shared 2 meters per second. Okay, so 13 is the change, plus 13. We take this fraction of 13. The minus sign is telling us that the velocity is decreasing for the player. That makes sense. So delta V for the person, 0.45 compared to 70. You take that ratio times 13, and I find that the player's velocity decreases by negative, or that's redundant, it decreases by 0.083 meters per second. Like we expected, not a very large change in velocity because people are much heavier than footballs usually. So then, since that's delta V for the player, I could say the velocity of the player at time 2 would be the velocity of the player at time 1 plus the change in the player's velocity. In other words, the original 2 meters per second minus the 0.083. And the player is still going at practically the same speed they had originally. 1.92 all around. Okay, well that's enough to notice, right? You'd still feel that. In fact, that 0.083, if I convert that to miles per hour, that's 0.2 miles per hour. I think you would sense that. Again, usually football players do not experience that because when they throw the football, their feet are still in contact with the ground, and so there's significant friction, and you can no longer make the argument that momentum is conserved. It would be a very different experience playing football while wearing ice skates. Okay, part B is a little different. Now we can say final velocity of the ball, this is what we're told, is 15 meters per second. This time it's with respect to the player, not the ground. So think about that for a moment. The player is still moving. Now the player is not going to be moving at 2 meters per second anymore because in the act of throwing the ball, they got a little push backwards, but they're still going to be going close to 2 meters per second. So the player's velocity of 2, close to 2, plus the extra 15. Remember, the ball is going 15 with respect to the player, but the player is already going at almost 2 meters per second. So the ball's velocity with respect to the ground is almost 17. Now, when you apply momentum conservation, this is a very subtle point. This equation came from F equals ma. F equals ma is only valid in what type of reference frame? A so-called inertial reference frame. You have to pick that reference frame and stick with it. So in this problem, the reference frame that we're using is the reference frame of the ground, not the person's reference frame. Imagine a set of XYZ axes attached to the player. What are these axes doing during the time that the player is pushing on the ball? Those axes would be slowing down. They would be accelerating. That's no longer an inertial reference frame, so we can't use that to apply this equation. That's a very subtle point. I don't know if that your book explored that, but just make sure you're being consistent in which reference frame that you're using. Okay, so we're still going to use this equation, or we could still use this equation, but I think this time I'll go back and start from here. Okay, so VB2. This is the velocity of the ball at time 2. Like I said earlier, in this problem, I'm using a notation where it's understood this is with respect to the ground. So this will be the player's velocity at time 2 plus what I'll call V relative. So if I were to adapt the notation from chapter 4, then let's get rid of the subscript 2. It's understood I'm talking about time 2. I would say VBG, the velocity of the ball with respect to the ground, is VBP, that's the velocity of the ball with respect to the player, plus VP, I'm sorry, I got those backwards. That would be, here, off to the side, VBG equals VBP plus VPG. Remember that rule with the subscripts? I stuck 2 P's in there. Velocity of the player with respect to the ground, that's what I'm calling VP2 in this problem. And VBP, the velocity of the ball with respect to the player, that's what I'm calling VR right now. I hope I haven't confused you further. I think this is a simpler notation because if I wanted to use this, I'd have to stick in the subscripts 2 as well. Do you see how one of the difficulties in physics problems is choosing an appropriate notation? Okay. This velocity relative, we're given that number. We're told that that's the 15 meters per second. Okay, let me go ahead and say total momentum before has to be total momentum after. And I've got the, well, before the throw, they move as one. So I can say total mass of the ball plus mass of the player times their shared initial velocity. That's the total momentum that they have as they move together. Afterwards, I have to break it into 2 pieces. There's the mass of the player, velocity of the player at time 2, plus mass of the ball times. Now, what I'm really writing here is the velocity of the ball at time 2, but I've just established that that's however fast the player is going plus the relative velocity. So you really have to be careful when you evaluate the various momenta. Make sure you get the velocities with respect to your reference frame, which in this case is the ground. What are we solving for? We're trying to figure out how fast the player is going after he's thrown the ball. And you might think about it for a moment. Is it still going to be, what was it, 1.92? Do you still expect the player to be going that fast? I would think of it this way. He launched the ball faster in part B. And that means he has to push harder on the ball. The ball was pushing back harder on him. I expect him to be going a little bit slower than this in part B. So he gave up some of his forward momentum to the ball. There was an exchange of momentum between himself and the ball. I think what I'll do is factor out the VP2 and I'll flip sides here. So I've got VP2 times mass of the player plus mass of the ball would be all of this, and then I'd have to subtract the one term that does not have VP2 in it on this right side. So that would be minus mass of the ball, velocity relative. And then the last thing to do would be to divide by this quantity. So the player's velocity after. You can see algebraically, this is coming out a little more complicated than part A. That was the difficulty with this problem, is the added complication of relative velocity. So can I contrast that with the equation I had from part A? Yeah, this is a little more straightforward. Okay, the total mass here, you know what, I think I'll just pause, evaluate this, and you can do the same and check. Here's what I find. instead of 1.92, of course, that's only 3 sig figs. If I were to round now, it would only be 1.90. So the difference is 0.02 meters per second. Not a huge difference, but detectable. So it does matter whether you specify the ball's final velocity with respect to the ground or with respect to the player.